Hi viewers, welcome to SG Know How channel. Here we have provided a video on solving the Towers of Hanoi with Python recursion. In this video, we will be exploring the Towers of Hanoi puzzle with Python recursion. So many of you would be wondering what is Towers of Hanoi. Before going into details, let's understand the Towers of Hanoi problem. The Towers of Hanoi problem is a classic mathematical puzzle involving three rods and a set of disks of different sizes. The objective is to move all the disks from one rod to another following these rules. Only one disk can be moved at a time. A larger disk can never be placed on top of a smaller disk. Only the topmost disk of a stack may be moved to another stack or an empty rod. The number of disks determines the difficulty of the puzzle. With more disks, the number of possible moves and the complexity of the solution increase exponentially. So in the Towers of Hanoi problem, we have three rods and a stack of disks. The goal is simple. Move all the disks from one rod to another following the rules that we have discussed already. To reiterate, let me tell you the rules once again. Only one disk can be moved at a time. Second, a larger disk can't go on top of a smaller one. And third, only the topmost disk of a stack can be moved. So the number of disks adds a twist here. The more disks, the trickier the puzzle. Let's tackle this step by step. So having seen what is Towers of Hanoi, let's give a solution to solve this Towers of Hanoi problem. Now it is a recursive approach with diagrams. We will explore the solution to the Towers of Hanoi puzzle using a recursive approach complemented by easy to follow diagrams. One of the most elegant solutions to the Towers of Hanoi problem utilizes recursion, which involves breaking down the problem into smaller, similar sub-problems. As we tackle the Towers of Hanoi, recursion comes into play, offering an elegant solution by breaking down the problem into smaller, similar parts. Imagine we have three rods A, B and C and a stack of disks of varying sizes on one of them. Usually it is A. Our goal is to move all the disks to another rod, usually the rod C, while adhering to the rules above. Figure 1 shows the initial state of the Towers of Hanoi with three disks on rod A. With reference to the figure, we can see there are three rods labeled A, B and C. Imagine disks of varying sizes are stacked on rod A. The goal is to move all these disks to rod C, adhering to the specified rules which we have discussed earlier. As shown in figure 1, this is the initial state with three disks on rod A. So figure 1 shows the initial state of the Tower of Hanoi. In the context of Towers of Hanoi problem, A, B and C are typically used to represent three different rods. Each rod holds a stack of disks and the goal is to move the entire stack from one rod to another following the rules of the problem. In solving the Towers of Hanoi, rods A, B and C symbolize the puzzle's dynamic components, guiding us to transfer disks following the specified rules. So with reference to this figure, let us designate the names for each rods. Rod A is called the source rod. This is the rod from which you want to move the stack of disks to the target rod. Initially, all the disks are on this rod. Rod B is called the auxiliary rod. This rod serves as a temporary storage location during the recursive steps of moving disk. It helps facilitate the movement of disk between the source and target rods. Rod C is called the target rod. This is the rod to which you want to move the entire stack of disk. The goal is to have all the disk end up on this rod. So in the Towers of Hanoi process, we see that A is the source rod, B is the auxiliary rod, and C is the target rod. A holds the initial stacks of disk, B aids in temporary storage, and the ultimate objective is to transfer all disk to C. So having understood what is Towers of Hanoi, let us now see how the Towers of Hanoi problem solving algorithm works. The base case is if there is only one disk, move it directly from the source rod to the destination rod. And the second case is the recursive case, which is for n disk. In this case, move n minus 1 disk first, that is, using the destination rod as a temporary storage, move the top n minus 1 disk from the source rod to the auxiliary rod. Next, move the largest disk. Move the remaining largest disk from the source rod to the destination rod. And last, move n minus 1 disk back. So using the source rod as a temporary storage, move the n minus 1 disk from the auxiliary rod to the destination rod. The Towers of Hanoi algorithm operates with the base case for a single disk, moving it directly to the destination. For n disk, it recursively transfers n minus 1 disk into the auxiliary rod, moves the largest disk to the destination, and then brings back the n minus 1 disk from the auxiliary to the destination rod. This is how the algorithm works. By repeating these steps recursively, we can eventually move all the disks to the desired destination while adhering to the rules. Figure 2 illustrates the solution of 3-disk Tower of Hanoi problem. So here n is equal to 3. Now figure 2 is a pictorial representation of the solution of 3-disk Tower of Hanoi problem. This approach guarantees the optimal solution with the minimum number of moves for any number of disks. The number of moves required for n disk is 2 power n minus 1. So we have understood that through recursive repetition, all disks reach the desired destination as shown in figure 2, which illustrates the solution for 3 disks in the Tower of Hanoi problem. This approach ensures an optimal solution with a minimum of 2 power n minus 1 moves for n disk. So let's bring the Towers of Hanoi to life using Python. In this section, we will dive into the implementation of Towers of Hanoi through an Python program. So here is a basic example of solving the Towers of Hanoi problem in Python using recursion. Now here we can see that the function to solve the Towers of Hanoi problem using recursion is given with the parameters as number of disks designated as n, source rod as source, target rod as target, auxiliary rod as auxiliary. And if n is greater than 0, then move n minus 1 disk from source to auxiliary using target as a temporary rod. Move the nth disk from source to target, and the third step is move the n minus 1 disk from auxiliary to target using source as a temporary rod. So the program defines a recursive function Towers of Hanoi that prints the steps to move disk from the source rod to the target rod using the auxiliary rod as a temporary rod. In the example usage, it demonstrates moving three disks from rod A to rod C. This Python code presents a simple solution to the Towers of Hanoi problem using recursion. The function Towers of Hanoi effectively moves disk between rods A, B, and C, demonstrating the process of transferring three disks from rod A to rod C. As we wrap up our exploration of the Towers of Hanoi with Python recursion, let's summarize the key insights and takeaways. The Towers of Hanoi is a classic mathematical puzzle involving moving disk between three rods following specific rules. The challenge increases exponentially with more disks, making it a fun and thought-provoking exercise. We explored the elegant solution using recursion, breaking down the problem into smaller, manageable steps. This approach guarantees the optimal number of moves and can be easily implemented in Python. So, in conclusion, the Towers of Hanoi presents a timeless mathematical puzzle. Its complexity grows with more disks, offering a captivating challenge. Our exploration showcased the elegant recursive solution, ensuring efficiency and simplicity, especially when implemented in Python. Thank you.